Now we know that why we are using calorimeter. There are four kinds of calorimeter: bucket or barrel calorimeter, then separating, throttling, and combination of separating and throttling. All these devices are used only for the sake of measuring dryness fraction. And dryness fraction is a index to measure the quality of your wet steam. If it is pure liquid, then there is zero dryness fraction. If it is pure vapor, then it is having a 1 dryness fraction 1. But if your steam is wet, then only the dryness fraction actually come in a role. So know how much steam is dry out of the total mass of steam, that is called the dryness fraction. Now here we will see how to measure by using separating calorimeter. Now as the name suggested, separating, that means it is just simply separate out moisture content and dry steam. So for this, imagine suppose there is a steam mill, that means steam pipeline. The supply of steam through this steam mill or steam pipeline. Now we are not taking directly that steam flow, so we have to use a sampling tube. Now sampling tube always having at the top some drill holes. That means your steam will enter through this drill hole and then enter to your sample carrying tube. So this is called sampling tube. So sampling tube. Now we must know what is the pressure, at what pressure we are taking this sample. So there is a pressure gauge. So pressure gauge, with the help of this pressure gauge we will measure the pressure of our sample. Then this sample is allowed to our calorimeter vessel. Now this sample is not directly allowed to get collected in an inner chamber. This is inner chamber. But there is one perforated cup. That means cup is there, but at the bottom there is some drill holes. So that is called perforated cup. So it is not directly allowing steam to enter in this inner chamber. So there is a perforated cup. This perforated cup only allow that drops, because whenever high pressure steam is striking on this perforated cup, so no doubt first direction change will be here at the bend. So due to direction change, whatever be the heavy water particles get separate out, and due to gravity definitely it is going to drop in this inner vessel. Secondly, whatever be the steam striking on this perforated plate or cup, that steam get change in its direction. So whatever be the steam coming out from this sampling tube, it gets changed in its direction, and due to this direction change, whatever be the heavy particles in steam, they left here due to heaviness, gravity, and they drop down and get collected, and we can say that this is the water content of that steam. So we are just using this perforated cup and this inner vessel to collect the separated water particles, separated, that is moisture content of a steam. Now after this, The outer body, now in outer body there is dry steam, because whatever the moisture content was there, it is remove out, separate out and get collected into inner vessel. Now in outer vessel there is only dry steam. Now this outer vessel having one opening at bottom, and this opening is allowed to exhaust that steam, dry steam, in a water bath. So suppose this is a water bath. This water bath having a known quantity of water. Suppose 2 liter quantity of water is there. And this water bath is kept on weighing scale. Now imagine, suppose I am taking some sample of steam from steam main with the help of this sampling tube. So whatever be the sampling tube having a sample, I have to control that. That means suppose I am taking sampling for 10 minutes. So later on I can measure what is the flow rate of that 10-minute flow, what is the mass. So I have to control that. Right now there is no controlling. So it is continuously supply of steam is there. Correct? So we have to provide one valve. Now this valve is simply controlling the flow. So suppose I am providing one valve here or this side. So this valve is simply to control the flow. So control valve. Now during experiment, I observed that this is my outer vessel, inner vessel, perforated cup. Then whatever be the outer vessel having one tube, and it is inserted into one water bath where known quantity of water is there. Then all this water bath is kept on weighing scale. Now imagine at the beginning, I will measure the weight of this water bath, because this tube is hanging. It is not actually supported on this weighing scale. So whatever be the weight is there, it is the weight of this water bath, correct? Now when I start my experiment, I will open this control valve and allow steam to enter into this separating calorimeter. So steam will enter as per the opening. Here I can measure the pressure. Then steam, first direction change is here at the bed. So no doubt some water droplets, moisture will separate out, and due to gravity it will slide down and get collected into inner vessel. After that, whatever be the steam is striking on this perforated cup, so there is again direction change. So again there will be a heavy particles, water particles will be separate out, and only dry steam will flow. So we can say this is a dry steam without any moisture. Whatever be the moistures are there, it is already separated. So this is dry steam. We are assuming, it is not 100% sure that this steam is only the dry steam, but we are assuming whatever be the moisture content is there, it is separate out and get collected into inner vessel. Whatever be the remaining dry steam portion, it is collected in outer vessel and pass through this water bath. This is, we can say, a condenser unit. because we are, this is a condenser. So this condenser unit having a water, so whatever be the steam entering into this water bath, no doubt it will lose its heat and get condensed, liquefied, and definitely we observe there is a rise in water. This rise in water is due to steam condense. So this is the mass of vapor, correct? Because this is the steam, dry steam. It don't have any moisture. Water particles are there, but it is get separated in inner vessel. There may be arrangement. Many times it having a drainage system. So many times we remove out this water with the help of drain wall. So whatever be the water get collected after my complete experimentation. So this water collected is drained out and I measure, that is our mass of water. Whatever be the dry steam, it get condensed. So whatever be the rise in water level in this condenser unit, we can measure the rise as well as we can measure the weight. So initial weight for the condenser unit and its known volume of water. Whatever be the increase in weight, it is nothing but a steam, dry steam. Correct? So from this we can measure quantity of water, we can measure the quantity of steam. And with the help of formula, dryness fraction is mass of steam divided by total mass of wet steam. Total mass of wet steam means mass of steam plus mass of water. Steam means dry steam. I am talking about the dry steam. Dry portion of steam, and this is the portion of water vapors. So we are separating water content and dry steam. Both we are converting into liquid form. So whatever is the separated water content of that wet steam, it is collected in inner vessel. Later on we can measure it, what is the quantity, what is the mass. Whatever be the dry steam is there, we are condense it in our condenser unit, and by the difference of weight we can come to know that what is the amount of that dry steam. And then putting into the formula, dryness fraction is mass of vapor divided by mass of vapor plus mass of water. So here we come to know how much steam is dry. Correct? It is a little bit more accurate than barrel, but still approximate method. Many separating calorimeter having a water level indicator also, and that indicator having one scale, and that is already calibrated in terms of kg. So there will be a one water indicator having one scale, having a calibration in terms of kg. So we can directly measure how much is the water content is there in terms of mass kg. Otherwise, we can drain out this and we can measure the weight, and we come to know what is the weight of steam. So this is separating calorimeter. So very basic, we have to separate out wet steam from dry steam. Then both we have to convert into liquid form, because in a steam form we can't measure the weight. So whatever be the dry steam, we are flowing through a condenser where already water is there. So when that steam mix with water, so it deliver its heat and get condensed. So definitely there will be a rise in weight of that water. So remember, again and again I am saying, only the rise in weight is the steam portion. Original, there is some weight of water. Rise in weight is the mass of steam. Clear? Now the next, more accurate than this separating calorimeter is throttling calorimeter. Now before going to throttling calorimeter, we must know some basic of throttling process. Why we are using throttling? Why there is a need of throttling process? Okay, what is the throttling? I think this much portion is already covered. Throttling process. What is throttling? Okay, let me simplify this. Suppose you having some gas, air, compressed air or compressed any different gas. Okay, and it is at high pressure and you want to reduce the pressure. So we know that we have to increase the volume. As the volume increase, pressure will decrease. Correct? So if there is any piston cylinder arrangement and there is a high pressure, gas is entrapped. So if I increase the volume of that piston cylinder arrangement, so pressure will be decreased. But some applications are there where we don't have provision or scope to increase the volume, but we require a decrease in pressure. So in that case, we have to use a throttle valve or throttling device. Now, throttle valve or throttling device is nothing but simply a small narrow opening. So whenever high pressure gas or any medium passing through that small opening, so it gets throttle out. So during throttling, because small opening is there, so we have to overcome that friction and we have to come into second side through that small opening. So during that, its pressure get reduced. And this is possible by either you have throttle valve. Throttle valve means your regular valve can be a throttle valve if you just simply open a little bit. So whatever be the pressure is there, it don't have that much area to flow. You are just simply opening a small portion of your valve, so it will be get throttle. Or you have any porous plug. So when there is a porous plug, so porous plug means it is a material which having a small openings, just like your bricks. So it having a very small opening. So through that small opening, when high pressure gas is tried to pass on, so its pressure get reduced. Now that reduction in pressure actually add the heat, and that addition of heat increase the temperature of steam. We are talking about steam. So let us first clear our idea. Suppose I am plotting a TP diagram, temperature versus pressure. Suppose I open a valve to a particular diameter. So I observe there is a throttling process and I am getting such curve, throttling curve. So this is suppose, and throttling operation, remember enthalpy remain constant. So this is H1 curve. So during this, throughout the curve, we observe that it is constant enthalpy. Next time I just increase the opening. Still there is a throttling operation, but now the orifice diameter is increased. So enthalpy remains same, but at different level. So I am getting a different curve. So suppose enthalpy 2 is there. Again I am increasing the opening. So again I observe some constant enthalpy curve. Suppose H3. So on this curve, H3 is constant before throttling, after throttling. So imagine, suppose there is a pressure line and meanwhile there is a one throttle valve. If I am measuring pressure here, suppose P1, and if I am measuring pressure here, so this is P2. So definitely after throttling, pressure will reduce. But enthalpy remains same. H1 is always equals to H2 because there is no change. But we are talking about Even though enthalpy remains same, but after throttling, our steam gets superheated. Suppose I am supplying steam here at suppose Raynaud's fraction 0.8. That means it is a wet steam. But after throttling, when I measure its temperature, so it becomes a superheated steam. How it is possible? I am decreasing the pressure, but still heat is generated, and due to that heat, temperature rises. So wet steam get converted into superheated steam. Now, how it is possible? Suppose I am plotting a pressure versus temperature. For throttling process, certain opening I am observing H1 enthalpy. So throughout this process there will be a H1. So enthalpy remain constant before and after. Now how we come to know what is the before and after? So there is an increasing slope and decreasing slope. But we observe one point where slope is 0. Just like the critical point. For this enthalpy curve, there will be a slope 0. For this, slope 0. This side, on right side, there will be a slope. But at certain point, there will be a slope 0. If I join all these slope, 0 point, so this is called inversion curve. And on this inversion curve, we observe mu is 0. Mu is 0. So what is mu? Mu is Joules Thomson coefficient. So inversion curve is a curve where we always observe Joules Thomson coefficient is 0. On this side, mu is positive. On this side, mu is negative. So we know very well that is there is some 0 point below 0. We assume that it is a negative side. Above 0, it is a positive side. But in this case, this inversion curve represents the Joules Thomson coefficient having all 0 points. On left hand side, this is having a positive value. On the right hand side, it is having negative value. That means we can say on left hand side, this coefficient having greater than 0, and on right hand side, it is lesser than 0. Correct? Now for hydrogen gas, this highest point where we observe Joules Thomson coefficient is 0, or we can say where slope is 0, it is about 68, minus 68 degrees centigrade for hydrogen. So for hydrogen, this point is minus 68 degrees centigrade. Now at this point, suppose this is the pressure. If I am supplying hydrogen, before throttling, hydrogen is at minus 68 degrees centigrade. Before throttling, it is having some pressure. After throttling, definitely its pressure will reduce. So before throttling, it is at minus 68 degrees centigrade. That means this is the pressure. After throttling, no doubt pressure will reduce. That means pressure is reducing. So after throttling, I am observing temperature is also reducing at this minus 68. Then again reduce. So after throttling, pressure reduce, temperature reduce. Correct? But now imagine if I am supplying hydrogen at suppose 10 degrees centigrade. Minus 68 means where Joule-Thomson coefficient is 0. If entry point of hydrogen is at minus 68, after throttling, no doubt pressure will reduce, because throttling process is reducing the pressure, correct? So as pressure reduces, temperature decreases. But if before throttling I am supplying hydrogen gas at 10 degrees centigrade, so no doubt 10 degree means somewhere here. So hydrogen gas I am supplying, it is having suppose this point and corresponding pressure is this. So before throttling, this is the pressure of hydrogen. After throttling, no doubt pressure will reduce. What about temperature? So temperature will increase. So height is increasing, that means temperature is increasing. So the value of Joule-Thomson coefficient actually decided during throttling whether your temperature will increase or decrease. Regarding pressure, definitely pressure will reduce. But what is the impact on temperature? So that temperature will rise after throttling or drop after throttling is depend on Joule-Thomson coefficient. So if you are supplying your steam or gas in this zone before throttling, so after throttling pressure will reduce, but we observe temperature is increasing. But if we are supplying our gas at this point, so after throttling pressure reduce, temperature also reduce. But in case of steam, we always observe that temperature is increase. So whatever be the wet steam we are supplying, pressure is reduced. But due to your Joule-Thomson coefficient lie in this side, so even pressure is reduced, but we observe rise in temperature and our steam becomes superheated. So is it clear now? So there is two effect, temperature decrease or temperature increase. And this is for real gas. Remember, real gas. It is only possible for real gas. If it is ideal gas, then this throttling process don't have any effect on temperature. Temperature remains constant. There will be a reduction in pressure, but temperature remains same. Isothermal process. But if it is a real gas, so there might be possible temperature will decrease after throttling or increase after throttling. In case of steam, we observe that even though wet steam is there, but after throttling pressure is reducing, but temperature is becomes superheated. Clear? So now we will see how throttling calorimeter is working. Many times your external will ask this, pressure reducing. So we have a general relation, PV upon T is constant. Correct? In throttling process, we are not changing the volume directly. There is not a piston cylinder arrangement. So in this regard, if we observe, so pressure is directly proportional to temperature. Correct? Then we are talking for throttling, pressure is reducing, so your temperature must be reduced. He always will make you confused, remember. So it is expected you know the basic. Pressure is reducing, that means definitely temperature will reduce. Is it correct? It is proven law. Then how you are saying there is possible that temperature might be increase or decrease? Just we saw it is possible that your pressure decreases in both the cases, but temperature will increase or decrease, it depends on in which zone you are supplying your steam. Correct? Either negative zone or positive zone. So accordingly, we observe the change in temperature. So what is your explanation? One side you are saying it may be increase or decrease, and your law saying if pressure decreases, so temperature decreases. Either both are correct, or one is correct, or both are wrong. Both are correct. So how you will justify? How will you defend it? No? Joule-Thomson coefficient and whatever the explanation. It is showing that it is decrease in pressure, but temperature either decrease or increase, depend on the where you are lying, positive zone or negative zone. But your law saying pressure is directly proportional to temperature. So either this law is correct or whatever be the explanation of your Joule-Thomson coefficient, accordingly, that concept is correct. Not at a both not at a time. Correct. That is your explanation. This is made for ideal gas. We are mixing two concepts. In ideal gas, this is correct, and in real gas, this is correct. Temperature either increase or temperature will decrease. So he just make you confused. So you know the basic. Whatever be the relation, we are talking about ideal gas. And in ideal gas, we just say that in throttling process for ideal gas, temperature remain constant. For real gas only, temperature either decrease or increase. It depends on your Joule-Thomson coefficient. Clear? So never be confused. रहेगा याद? Now we will see how throttling calorimeter is working. So we have to just have that throttling operation. So suppose this is our steam main. So this is your main steam pipeline. So through this we are just taking one sample. So we therefore sampling tube. Sampling tube, but here we are not putting a control log. We are first putting a pressure gauge. So we must know what is the pressure before throttling, because after throttling pressure will decrease. So before throttling, so this is pressure gauge. Which measure the pressure of steam before throttling. After that, we are providing a throttle valve. This throttle valve is not a regular control valve. It is a throttle valve. That means just providing a small opening. So throttling process will be possible. So control. This is throttle valve. And after this throttle valve, whatever will be the outlet is supplied to one chamber. Now there are three kind of chamber. First is inner chamber, and in this inner chamber we are putting a thermometer. The thermometer is there. Then this steam will enter into second chamber. And then in last outermost chamber. And this is covered with a lid which is insulated. This kind of arrangement is there. Now here the inner chamber, if possible, some water droplets or moisture get separate out. Even though we are saying it is after throttling a superheated steam, but meanwhile temperature may reduce, may reach to saturation, may be possible heavy drops is there, so it gets separate out. Otherwise, we don't observe any liquid particles here. But if anything is there, there may be a connection in inner tube only, and later on we can remove. But it is observed that we never obtain any liquid particles in inner chamber, especially in throttling, because it is simply a superheating process. Now, here we have to provide one manometer which is measuring a pressure after throttling. So this is P1 initial condition. This is P2 for P2. It is not directly measuring pressure. We are just getting a manometer reading in terms of column. So suppose, okay, what do you think? Which column having a higher level of your manometer liquid? Right or left? Yes? Right. So after throttling, pressure will reduce. That is correct. So which column? Left. Get confused again. Remember, your external will confuse here only. Always remember, no doubt, whatever be the boiler you having, whatever be the steam generated, definitely having a high pressure. After throttling, that pressure will reduce, but still that pressure remain above atmosphere. It will never decrease. Manometer, if it is in idle condition, if it is not in working, so manometer fluid will be at the same level, correct? But after throttling, still there is a higher pressure than atmospheric. So no doubt your column rise in this direction only. So we are getting manometer reading. So remember, still it is a manometer, but whatever be the pressure after throttling, it is not going below atmospheric. If it is going below atmospheric, then only this column will rise. Still there is a high pressure, at least above atmosphere. So whatever be the high pressure is there, it will shifted this manometer fluid on second side only. Clear? Okay, now this steam, we are taking the steam from this sampling tube. We will measure that pressure with the help of pressure gauge. Then we will throttle this steam with the help of this throttle valve. Now after throttle valve, definitely steam will enter into this main chamber, innermost. But this is superheated steam. Temperature will rise. Why rise? Because during throttling process, pressure is reduced. The reduction of pressure having an impact of increasing temperature. Of temperature क्यों बढ़ता है तो always remember there is an addition of heat. So drop in pressure during throttling actually increase the heat, and due to that heat, temperature rises and we obtain a superheated steam. Now this superheated steam enter into this first innermost column. Here we can measure what is the steam temperature. So here we can measure, it is suppose this much level of temperature, and that is the superheated steam. Then this steam will travel into second inner chamber. Still it is in a steam form. As I said, we never obtain a liquid particles separate out, because this is not a separating calorimeter. Otherwise, there will be a separation of water droplets. So steam already at superheated. but due to direction change, we are not observing any water separation. And in last, it is exhausted in steam form only, and there is no need to provide any condenser to measure how much is the steam. But because we are using throttling correlations, empirical relations. Now here, this is throttle valve, this section is suppose 1, this section is second. We know that during throttling, enthalpy remains same. So whatever be the enthalpy before throttling is always equals to enthalpy after throttling. Correct? Now, before throttling, it is assume a wet steam. But remember, this apparatus is not suitable for higher wet steam level. It is for lower wet steam. That means 0.8, 0.9, that much wet steam, okay. But you are providing a steam at 0.3, 0.5, then it is not working for this. Because that wet steam, even though it will not convert into T super. If your throttle valve not converting your steam into superheated steam, then it is not going to give any kind of readings, correct readings. Why? Because if it is not a superheated steam, after this traveling, your water content will separate out. Then it behave like a separating calorimeter. So throttling calorimeter is only possible. It gives the accurate reading when your steam gets converted into superheated. And for this conversion, your wet steam quality should be maximum dryness fraction. That's 0.8, 0.9. Likewise, that much steam we have to provide. So before throttling, so wet steam is there. We don't know how much is the wet. So HF 1 because it is before. 1 stands for before. So enthalpy of fluid when it is a liquid plus dryness fraction into enthalpy of HFG. So this is total enthalpy before throttling. After throttling, Hg, 2 stand for second part after throttling, because it become completely vapor. No doubt, steam is superheated, that means it is in vapor form. Now, the degree of superheat, we have to consider that also. It is not a dry saturated vapor, it is superheated. So, degree of superheat we should consider. So, it is Cps into T super minus T saturation. In terms of enthalpy, we can say H super minus H saturation. But here we can measure the temperature. So we must know what is the specific heat of steam, that superheated steam. What is the temperature of superheated steam? T saturation. How we come to know T saturation? This right hand side is belongs to after throttling. After throttling, we have a manometer. With the help of manometer, we can measure pressure P2, and from steam table corresponding P2, we will measure T saturation. And all these values corresponding to initial pressure. As this calorimeter is meant for measuring dryness fraction, so we have to measure this. That means it will unknown. If it is unknown, we must know the all other remaining values. So HF1, HFG1 corresponding to P1 temperature, Hg2 T saturation corresponding to P2 temperature, T super we can directly measure with the help of thermometer. Now Cp of that steam, it is 2.1 kilojoule per kg Kelvin. Standard. But if your numerical giving some other value 2.3, so we have to take 2.3. If it is not provided, then it is a standard 2.1. It is average. Standard means it is not a fix. But averagely we take this 2.1 as a CP of superheated steel. Now, once we have all the data except this X, shift all remaining data, we can calculate the dryness fraction of this steel. But as I said, it is not useful for more weight steel. Its advantage is it is more accurate, correct? And it fails to give reading if your throttling operation fails to convert your steam into superheated zone. And steam is behaving like a real gas. So whatever be the explanation of that Joule-Thomson coefficient is applicable for this steam. If it is a air, compressed air or any air fluid or any ideal fluid, then this concept will not hold good. It fails because ideal fluid, your temperature remains same during throttling. If temperature remains same, so there will be no temperature change, isothermal process. And this whole apparatus is made for real gases.